Okay, hey guys, welcome back. And today I'm going to be talking about Einstein's theory of general relativity. So, this is the introduction. In 1905, Albert Einstein determined that the laws of physics are the same for all non accelerating observers, and that the speed of light in a vacuum was independent of the motion of all observers. This was called the theory of special relativity. It introduced a new framework of all of physics and proposed a new concepts of space and time. Then Einstein had spent 10 years trying to include acceleration in the theory and published his theory of general relativity in 1915. And in that, he had determined that massive objects cause a distortion in spacetime, which is called as gravity. So now we're going to be talking about the tug of gravity. So what is gravity? Two objects exert a force of attraction on another, and it's called gravity. So Sir Isaac Newton quantified the gravity between two objects when he formulated his three laws of motion, which is which means like this part out. The force tugging between two bodies depends on how massive each one is and how apart the two lie. Example, let's take the earth and let's take any random person. The earth is pulling you towards it, with that which is what keeping you firmly lodged on the ground. Your center of mass is also pulling back the earth, but because of your smaller mass, the earth can uh, have an effect on you. Uh, have an effect on you. But because of the Earth's massive body, massive body, it barely feels our tug. Yet, Newton's laws assume that gravity is an innate force of an object that can act over a distance. Okay, before this, Albert Einstein, in his theory of special relativity, had determined that the laws of physics are the same for all non accelerating observers. And he showed that the speed of light within a vacuum is the same, no matter the speed at which an observer travels. And as a result, he found that space and time were interwoven, like they were combined to into a single continuum, which was called space-time, and that's why this theory is also called the space-time distortion. Events that occur at the same time for one observer could occur at different times for another. As he worked out the equations for the general theory of relativity, yeah, Einstein realized that massive objects cause a distortion in spacetime, like I had told in the introduction. Okay, imagine this. There's a imagine you put a large body in the center of a trampoline. The body would press down the fabric and it would dimple. A marble rolled around the edge would spiral inward the body. I'm pretty sure many of you must have seen that, right? So yeah, and it will be pulled in much the same way that the gravity of a planet pulls at rocks in space. Okay, now we are going to talk about experimental evidence. This is a very long part of this video. So, although instruments can neither see nor measure space time, Several of the phenomena predicted by its warping have been confirmed. Einstein's cross is an example of gravitational lensing. In case you want to know what is Einstein's cross, the picture which you can see is what it is. So Einstein's cross, which is a quasar in the Pegasus constellation, is an excellent example of gravitational lensing. The quasar is about 8 billion light years away from Earth, and it sits behind a galaxy that is 400 million light years away. Four images of the quasar appear around the galaxy. Why? It's because of the intense gravity of the galaxy, which bends the light coming for the quasar. Okay. Okay. So gravitational lensing can allow scientists to see some pretty cool things, but until recently, what they spotted around the lens has remained fairly static. However, since the light traveling around the lens takes a different path, each traveling on over a different amount of time, scientists were able to observe a supernova occur 4 different times as it was magnified by a massive galaxy. And a supernova is a pretty cool thing to me. I don't know about you guys. And in another interesting observation, NASA's Kepler telescope spotted a dead star known as a white dwarf orbiting a red dwarf in a binary system. Although the white dwarf is more massive, it has a far smaller radius than its companion. The technique is equivalent to like spotting a flea on a light bulb 3,000 miles away. Okay, instead of flea, you can think of a flash. So, roughly, it will be like the distance from Los Angeles and New York City. And this was told by Avi Chopra of the California Institute of Technology. Oh yeah, changes in the orbit of Mercury, which is shifting very gradually over time due to the curvature of space-time around the massive sun. In a few billion years, it could even collide with Earth. And okay, so frame dragging of space-time around rotating bodies. The spin of a heavy object such as Earth should twist and distort the space-time around it. In 2004, NASA launched the Gravity Probe B, also known as GPB, the precisely calibrated satellite. The precisely calibrated satellite caused the axis of gyroscopes inside to drift very slightly over time, a result that coincided with Einstein's theory. Okay, imagine okay, imagine the earth as if it was immersed in honey. You can imagine that. As the planet rotates, the honey around it would swirl. And it's same with space and time. This was told by Gravity Probe B Stanford University. GPB confirmed two of the most profound predictions of Einstein's universe, and far reaching across astrophysics research. So, now let's talk about gravitational redshift. The electromagnetic radiation of an object is stretched out slightly inside a gravitational field. Think of the sound waves that emit from a siren on an emergency vehicle, as you can see the ambulance on the picture. As the vehicle moves towards an observer, sound waves are compressed, but as it moves away, they are stretched out or redshifted. This is known as Doppler effect. The same thing happens with waves of light at all frequencies. In 1959, two physicists, Robert Pound and Glenn Rebecca, shot gamma rays of radioactive ion at the side of a tower at Harvard University. Yes, the famous Harvard University. And found them to be minutely less than their natural frequency due to distortions caused by gravity. Yeah, so gravitational waves. Violent events such as the collision of two black holes are thought to be able to create ripples in space-time known as gravitational waves. In interferometer, laser interferometer, Gravitational Wave Observatory, also known as LIGO, announced that it found evidence of these telltale indicators. In 2014, scientists announced that they had detected gravitational waves left over from the Big Bang using the background imaging of cosmic extragalactic polarization, which is BICEP2 telescope in Antarctica. It is thought that such waves are embedded in the cosmic microwave background. However, further research revealed that their data was contaminated by the dust in the line of sight. Now, without taking much of your time, I would like to tell you guys that to know more, type space.com theory of general relativity, and as you can see, just click that link, the first or the second one. I trust you guys that will be good if you want to know more.